Hi, my name is Dr. Padilla. I'm a professor of computer science and psychology, and I study how people reason with data visualizations. In this channel, we talk about all things data visualization related, and we have finally made it to one of my favorite topics, and it's actually what I study, and that's uncertainty visualization. In this video, I'm going to tell you about 5 uncertainty visualizations that you need to try. Okay, so I wanted to begin by going over this figure in a review paper that I, along with Matthew Kay and Jessica Holman, published. In this paper, we review the modern uncertainty visualization types and give you some advice about which ones to use and why. The first thing I wanted to cover is the most common type of uncertainty visualizations that exist, which are summaries of distributions. Let me give you some examples. So here we have a visualization that shows a placebo and a treatment, and it shows the infamous 95% confidence interval. This is the most common way that people represent uncertainty. It might be the only way that you know to represent uncertainty because it's so ubiquitous. By and large, it's what you see in most types of scientific publications, scientific reports. If they're showing uncertainty, this is the way that they're doing it. And most of the time, what is being represented here is a statistic. It is showing a mean representation. And what these bars are indicating is that we are 95% confident that the true population mean is at this mean here. Okay, so there's a lot to say about statistics and how we generate all of this information. The real goal of this video is just to give you a high-level overview of some of these visualization techniques. So I'm not going to go into detail about all these statistics. I'm just going to compare and contrast to give you a flavor of things that you can try. But in any case, this is the 95% confidence interval. Now, we have discussed ways to evaluate the expressiveness of a visualization as a method of determining how effective it is. So we might ask, does this express all of the facts and only the facts in the dataset? If you're unfamiliar with this term expressiveness, take a look on this other video that I made that's all about understanding what expressiveness is. But we want to understand, is it representing all of the facts and only the facts in the visualization? Well, one of the issues with error bars is that they aren't always consistently showing the same thing. It is a summary statistic, and we're showing, in this case, 95% confidence intervals. But we could show standard deviations, we could show standard error. The actual range of this interval can change, and oftentimes people do not know how to interpret these. What research finds by and large is that experts and the general public misinterpret these error bars most of the time. They're very, very challenging for people to understand. Let's do a little example. Here are 2 95% confidence intervals. I've shown this in a previous video, so you might know what's coming. If you were to look at these intervals, you might not realize that the underlying data that generated these intervals is very different. One is a normal distribution and one is a bimodal distribution. So it is hiding important features of the data because it's averaging over this distributional space. Now, there are even more problems with these types of confidence intervals. Research also finds that people are really biased by this interval itself. People think that values are more likely to fall within this bar than above the bar, even though these are just intervals around the mean. You might not understand all of this exactly, but I just want to highlight all of the issues with these types of bars. The last thing I'll point out, and there are many more, but the last thing I'll point out with these intervals is that people also think that values just inside the bar are more likely than just outside of the bar. They really look at this kind of end cap and think that there's something profound when it is showing distributional data. It doesn't appear to be distributional, it appears to be categorical. We think that this is a range and there's nothing outside of this. If I go back to this example, these intervals are created from distributional data. The data underlying these intervals is distributional, but that's not how people see it. They see it as categorical. Okay, so there are lots of issues with intervals like these here, both error bars and box plots. So instead, you can use a distributional visualization to show your distributional data that gets around some of the issues with these intervals. Now, there's lots of caveats and this work is very much emerging. So I'm just going to give you a flavor of what these are, and make subsequent videos that really talk about the nuance of each of these techniques. But I want to get you exposed to these and give you some resources so you can look up how to go ahead and try to make some of them on your own. Okay, so let's look at some of my favorites to start. On the top, we have a density plot here, and on the bottom, we have a quantile dot plot. And these are both showing distributional information, continuous information. But we want to think about how effective these different techniques are, meaning how easily and readily can you read off values from these visualizations. So a task that we might do with this is we might ask, what is the probability that the temperature will be 32 degrees or lower? Here or lower, and this is the nightly forecast, and the nightly forecast here, okay? So this is a density plot, a distribution. The way that you would have to do this calculation is you would have to find 32 degrees on the chart and mentally do an integral under the curve. Maybe you can do that. Some people can do that. That can be very challenging. This is certainly more informative than if it was just an interval, but this particular calculation can be quite challenging. If we look at this bottom version here, which is a quantile dot plot created by Matthew Kay and colleagues, what it does is it takes this continuous area and it breaks it into quantiles that gives you discrete information for which you can count, basically. So what you can do is you would learn that each of these dots represents a 5% probability, and you can count up. You can say 5, 10, 15, maybe somewhere between 15 and 20. You can do kind of a rough estimation. And if you knew a little bit about how these are created based on a cumulative distribution function, which is shown at the top. You don't have to know this visualization. I'm just illustrating to you. But what you can do is you can find 32 degrees and work backwards to find the explicit probability, which is 16%. Okay, so that's a lot of very complicated underlying math, and we were able to get close to that approximation by counting these dots. And that is really the beauty of this particular technique, is that it does not require complicated statistical knowledge. It allows people to do a strategy, and the strategy just so happens to get people to the right answer, which is fantastic. That means that it's very effective in terms of helping people come to the right solution. Okay, so that's a really cool technique called a quantile dot plot. I showed you a density plot, which is a version of this violin plot. A violin plot is a reflected version of the density plot. It has both sides, but it's pretty equivalent. The next thing I want to show you in terms of a cool uncertainty visualization technique that you might consider trying is a hypothetical outcome plot. Okay, what is the hypothetical outcome plot? What it is a animated way to convey distributional information. What I'm showing you here is each of these lines are animated draws from a distribution. We have a gray distribution here and a purple distribution here. And each one of these lines is sampled from a distribution. And you're shown this in an animation. If you have issues with seizures or anything like that, you might want to skip ahead in this video. I'll have an indicator of what you should skip to because I am going to be showing animations for the next few minutes. Let's look at what it looks like without the underlying distribution. Here is a hypothetical outcome plot, and it's showing 4 different distributions represented with each of these different colors. So what I would like you to do is to look at this hypothetical outcome plot, and I want you to try to imagine what the underlying data looks like by just looking at the animation. See if you can start to understand where these individual pulls from the distributions are. Let me just clarify. Each time that the animation moves around, each one of these jumps essentially is one selection from this distribution. So because it is a distribution, it is going to have more selected in the middle, less selected out of the sides. You can kind of see that, right? We're going to see more lines here, more lines over here, a few out to the tails, okay? So that's going to be the case with the next one, but I'm not going to show you the underlying distribution. Okay, I want you to imagine what the distributions look like for these 4 different distributions in this data set. I'll give you a few seconds to do that. Just picture it in your mind. Are you starting to see it? Okay, here are the distributions that these individual lines are pulled from, and you might have been able to visualize that each of these lines is kind of building up these different mountains that make a distribution, which is really cool. That's really the power of these hops visualizations. It also has the added benefit of conveying implicitly uncertainty. It is giving you this sense of uncertainty because you can't really focus on any specific value. You're getting a sense that the data is moving around, which can be really, really useful. In part because people tend to ignore the uncertainty if they can and try to just focus on a specific value. So hops are a really cool method to help people more effectively do that. Here's what a hops version would look like, a version that just shows a mean, 95% confidence intervals, a version where we're showing intervals but 4 different standard deviations, and then the density plots. So you can see that there's a whole array of different techniques that you might use, and truly they all have pros and cons. I showed you hops because I think they're cool and I want more people to give those a shot, but there's certain caveats. If you are prone to seizures, absolutely do not use these. If you don't have a good internet connection and you need people to look at a static visualization, don't show these. If people only have a few seconds to look at them, hops aren't going to work because you need the animation to play over a little bit of time for people to build up the distribution in their head. But it is a cool technique that I think you should consider when you're thinking about uncertainty visualizations. I want to point you to this really cool resource. This is ggdist, and it is in R, of course, but the nice thing is that it shows you different uncertainty visualization techniques that I described here and some more, and it gives you code, of course, to produce them within ggplot. This is by Matthew Kay at Northwestern, and there are lots of really interesting vignettes that illustrate why you might want to use one of these techniques over another, and lots of cool techniques that might inspire you. So definitely take a look at that if you're using R or any other programming language. The last one that I'll highlight is really cool, has received less examination empirically by research studies, but I think it's really neat and I want to show it to you. And this is a way of using color to represent uncertainty. So what we have here is a baseline data map and an uncertainty map. This is essentially showing error across these different values. Now, how do you combine these two things? The tricky part about uncertainty is it's often a second layer that's applied in addition to a particular value. You might have uncertainty in terms of voting election results, or you might have uncertainty in a weather forecast. So you have the weather forecast plus the uncertainty. So there's 2 levels there. This is a really cool way using color to integrate the primary thing that you're trying to communicate and uncertainty. So the first one is a bivariate color map that uses uncertainty. And what it is simply done is it's mapping uncertainty here with the saturation of the color, where the lighter the color is, the more uncertain it is. Okay, and that is fine. You can do that. That's just kind of a one-to-one mapping where you have households using the snap, and then you have margin of error. The really cool one, though, is this value suppressing uncertainty map. And what it does, if you notice down here, is that it collapses values for which the data is uncertain. That means that when there's high levels of uncertainty, it is actually harder for the reader to figure out what amount of households are using Snap. So what it essentially does is it forces people to be more conservative in their judgments when there is high uncertainty. Very cool, right? There's lots of caveats for that. One is it's literally making the visualization harder. So in some ways that is failing the effectiveness principle. But I think it's a really interesting option that you might want to consider. Of course, don't use it in all cases, but I just wanted to bring it to your attention. Okay, here's a summary of the visualization techniques that I've talked about today. I have not discussed this one down here, which is an ensemble plot and a multiple forecast visualization. That is actually what I studied, that particular technique. And I didn't want to include it here because I think it needs a whole video onto itself. It is subtle, these types of techniques, and I think there's a lot of ways to do it wrong. So before I recommend taking a look at it, I want to go ahead and unpack all the caveats for those types of techniques. But I definitely think you should take a look at some of these other ones that I talked about. In particular, the most stable will be this quantile dot plot and this density plot. There has been probably a dozen, maybe half dozen studies at this point finding that the quantile dot plot is among the most effective visualizations that they've tested, comparing many different visualizations. It also works really well with people that have low working memory capacity, that's ability to store information in the mind, and it's just very, very stable. I've done many studies that I haven't published as well, and they always come out to have the result that the Quantile dot plot tends to have the most superior performance. So I think that's really stable. On par with that tends to be this density plot. Now, there's situations where those might not work. So you might want to consider some different visualizations as well. There's quite a bit of support for hops, but again, there's many caveats that correspond to if you can't support this animation, how much time people have. Gradient plots, I think, are an interesting option as well, but in some ways they can be versions of intervals, which I'm always against, in part because if you have a true gradient, a Gaussian blur, on some people's monitors, you will see banding, and that banding will create a perception of intervals that is inconsistent across browser screens. So what you need to do is you actually need to have these hard intervals to make a perception of a gradient. And all of a sudden, you're now looking at the issues with intervals, even if they're very small intervals. So I have a major caveat there. You've already heard my caveats for the value suppressing color palettes, and I'll talk more about ensemble plots in future videos. But I hope this was fun. This is truly my favorite topic, and I think it's very unfortunate that people tend to learn about uncertainty visualizations at the end of the course or, after they made it through the more simplistic plots. But I think it is really important to understand how to read uncertainty visualizations, particularly because we're in a world where we're faced with more uncertainty every day. Uncertainty in politics and stocks and weather, and it's only going to become more uncertain. So it's pivotal that we both know how to represent uncertainty very well and know how to read uncertainty effectively. If there's anything specific you'd like to know, please comment about that, and I will do my best to make videos for those specific topics. Thank you for watching, and take care.